I'm Lucas, and this presentation will be on a proof for Cauchy's mean value theorem, L'Hopital's rule for limits in the form of 0 over 0, and why the classical equation of kinetic energy is a good approximation at non-relativistic velocities. So firstly, for Cauchy's mean value theorem, we're going to assume two functions, f and g, and they have the following properties. They're both continuous on a closed interval AB. They're both differentiable on the open interval AB. And g prime of x is not 0 for all x in the open interval AB. And so what Cauchy's mean value theorem says is that there exists at least one point, which we'll call C, in AB, such that f of b take f of a on g of b take g of a is equal to f prime of c on g prime of c. So for our proof, we're going to define some other function, h of x, which will be defined by this. And this k here is defined as this constant here. What we're going to do is we're going to apply Rolle's theorem here, and this function, the Rolle's theorem on h, and this is valid because h is continuous on AB, the closed and bounded interval AB, and because h is a linear combination of functions, and h is also differentiable on the open interval AB because it's a linear combination of two differentiable functions. And so applying Rolle's theorem, differentiating h, we get h prime of x is equal to f prime of x take k times g prime x. And what we notice is that h of a is going to equal f of a take f of a take k g of a take g of a. This is equal to 0, and that h of b is equal to f of b take f of a take k g of b take g of a. And once we expand out k here, we see that the denominator of k, g of b take g of a, is going to cancel out with this part of the function here, and that leaves f of b take f of a minus f of b take f of a, which is also 0. And so we find that h of a is equal to h of b, and that's equal to 0. And so with this, we've satisfied all parts of Rolle's theorem, and so we know that for, if we call this 1.1, there must exist some value of c in AB such that h of c is going to equal 0. Sorry, h prime of c is going to equal 0. And then we have that 0 is equal to f prime of c, take k times g prime of c. So after applying Rolle's theorem, this is what we get. So there's some value of c that is contained in AB, such that h prime of c equals f prime of c take k times g prime of c. And what we're going to do is just focus on this part here, and then we can show that f prime of c is equal to k times g prime of c. And if we remember that we've defined k as f of b, take f of a, over g of b, take g of a. So here we can just isolate k to find that f prime of c over g prime of c is equal to k, and expanding out into k, we find our result, and that's that f prime of c over g prime of c is equal to f of b, take f of a, over g of b, take g of a. And so this is the end of the proof for Cauchy's mean value theorem. As you can see, all we had to do was define some auxiliary function and apply Rolle's theorem, and we get to the result we were looking for. And with this result, we are going to prove L'Hopital's rule. So now we suppose two functions again, f and g, and these are differentiable on some open interval I, which contains a, except for possibly at x equals a. And so we want to define these conditions first. The limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is also equal to 0. And our second condition is that g prime of x is non-zero for all x in our interval I, except possibly at x equals a. And so for our third condition, we're going to find the limit as x approaches a of f prime of x over g prime of x exists, and it's L, and L can be any finite real number, infinity or negative infinity. Then, what L'Hopital's rule tells us is that the limit as x approaches a of f of x over g of x is actually equal to the limit as x approaches a of f prime of x over g prime x, and this is equal to L. So, you know, there's the same limit we've defined in condition 3. And so here's the proof. Given the first condition, which was that the limits of both f and g as x approaches a is equal to 0, we can define two new functions. Capital F of x is defined such that it is equal to f of x for all x in the interval I, except for at x equals a, and is equal to 0 at x equals a. And so capital G of x is defined similarly, where all I have to do is change this into a big G, and change this into a big G. So we've done this so that they're continuous at these points. And so with this, we two new properties emerge. F and G are both continuous at A, since the limit as x approaches A of capital F is equal to the limit as x approaches A of capital G, which is equal to capital F at A, which is equal to capital G at A, which is equal to 0. And our second emergent property is that f and g are differentiable on I, with capital F prime x equaling f prime x and capital G prime x equaling g prime x. And so, without any loss of generality, we will consider the case x is greater than a. And so the argument for x is less than a is very similar. It's identical, pretty much. But to save on time, we're just going to consider this. And then we're going to look at this new interval. So we're considering x is greater than a, and x is, within this interval I that we've defined before. But now we're just considering the closed and bounded interval ax. And so what we're going to do is apply Cauchy's mean value theorem to f and g, and the conditions to apply this theorem are met because capital F and capital G are continuous on this interval AX. Capital F and capital G are differentiable on this interval AX, this open interval AX, sorry. And from our second hypothesis, from this condition 2 and the previously defining condition, if we consider big G prime of t, for some t, well, it's equal to little g prime of t, and there's no value of t such that these are equal to 0. And so with this, we can apply Cauchy's mean value theorem. So following from this, by the Cauchy mean value theorem, there must exist some Cx in this open interval Ax such that capital F of x take capital F of A over capital G of x take capital G of A is equal to capital F prime of Cx over capital G prime of Cx. And so substituting for, by definition of our capital F and capital G functions, capital F of x is equal to f of x, capital F of A is equal to capital G of A, which is equal to 0, and capital G of x is equal to little g of x, capital F prime of C of x is equal to little f prime of C of x, and similar for G. Substituting this into 1.3, we get this. F of x takes 0 over G of x takes 0 is equal to f prime of C of x over G prime of C of x. So now we're going to consider squeezing this interval more and more, right? Because we're trying to find the limit as x approaches a. So as x approaches a, we have like this little inequality here, C of x, which is less than or equal to x. For x is greater than a. If we were considering x is less than a, it would similarly be x is less than C of x, which is less than a. But since we're only considering for x greater than a, we don't have to worry about this part. And so we then find that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime c of x over g prime c of x. So by doing this, we're squeezing this interval even smaller and smaller and smaller, such that c of x is actually approaching a, right? And so this is actually equivalent to the limit of c of x approaching a of f prime c of x over g prime c of x. And so this is going to be equal to L, and then therefore we deduce that the limit as x approaches a of f prime of x, of f of x over g of x must be equal to L. So obviously all we've done here is stuck a limit on both of these sides such that we're taking x to approach a, and so we get this equation here, and since c of x is approaching a, and because of this inequality here, it's actually equivalent to writing the limit as c of x approaches a of this, and this is going to be equal to L, and since this is equal to our original limit here, we find that the limit as x approaches a of f of x over g of x must also be equal to this L. So these limits, they are equal to each other, which is a very useful and handy result, as I will soon show. So here is my physics application for specifically L'Hopital's rule, and that's the classical limit of relativistic kinetic energy. And so we, in special relativity, defined kinetic energy as this formula here, and that's gamma take 1 times m naught c squared, where m naught is the rest mass of like some particles, c squared is the speed of light squared, and gamma is the Lorentz factor, which is 1 over the square root of 1 take v squared on c squared. And so once we substitute this back in, we get this, and if we let this term beta equal v on c, then we have that the kinetic energy is equal to m naught c squared 1 take b squared to the power of -1/2 take 1. We want to show that for very small non-relativistic speeds, i.e. v is very less than c, or we could say as beta approaches 0, this formula actually approximates the classical formula for kinetic energy, which is k is equal to half mv squared. So for this, we're going to consider the limit as the velocity approaches 0 of the kinetic energy over this classical formula equaling to 1, or equivalently, the limit as beta approaching 0 of the kinetic energy over a relativistic formula equaling to 1. And so we're looking at the kinetic energy, right? And we're analysing for small beta. So we're going to call this limit L. And this is equal to the limit as beta approaches 0 of the kinetic energy, the relativistic kinetic energy, over b squared. And this might look a little weird at first, but I promise at the end, it shows our result. And so if we're looking at this with direct substitution, as beta approaches 0, what we get is, if beta equals 0, this is just going to turn into 1 take 1. So this entire numerator is going to equal 0. And the denominator is also going to be equal to 0. And that puts us into indeterminate form, right? But luckily, as we just proved, L'Hopital's rule can be used when we get this sort of form. So, and to do this, I'm going to define another auxiliary function. So here I've defined the numerator and the denominator as two functions. And that's going to be n of beta, which is equal to the numerator here, m naught c squared times 1 take b squared to the -1/2 take 1, and then d of beta to be equal to the denominator, beta squared. And so what happens is, once we differentiate these two functions, we get this here as a result. Sorry, got a bracket there. And differentiating d of beta, we get 2b. And so once we take, according to L'Hopital's theorem, this is equal to L, which is our original limit here. And so the limit as beta approaches 0 of the derivatives of these two functions is equal to the limit as beta approaches 0 of m naught times c squared beta 1 take beta squared to -3 on 2. This is divided by 2 beta, because that's d prime at beta. And what we actually can do here is cancel out this beta, cancel out this beta, and then what we get is L is equal to the limit as beta approaches 0 of m naught c squared of 1 take beta squared to -3 on 2. And then we can just use direct substitution to show that this means the limit is equal to m naught c squared over 2. And so, therefore, we conclude that for very small beta, and that i.e. v is very, very less than c, we have that k on beta squared is equal, not equal to, but approximately equal to half m naught c squared. And we can bring this across to show that we can bring this beta squared term across So that's k is approximately equal to half m naught c squared. And then we're actually going to put beta in terms of what it actually is. So that would be v squared on c squared. As we see, c squared cancels out with c squared. And then we come to our result. And that's that k is approximately equal to half times m naught v squared, which is exactly the classical derivation of kinetic energy, which is really cool, because this is a formula that was derived in the 1600s through empirical evidence, and through Einstein's theory of special relativity, we can actually show why this worked, why this classical approach worked, and and why it was good enough in our everyday models to believe that it was right. Because in the 1600s we weren't dealing with speeds close to the speed of light. They didn't even know what the speed of light was. And so yeah, I think this is very cool, and is a very neat application of L'Hopital's rule, which was originally derived from the Cauchy mean value theorem. And so yeah, that concludes my presentation. I hope you enjoyed. Sorry, I was a little bit all over the place, a little bit sporadic, but yeah, I hope you liked the example.